objects, so one can think of Darwin's finches. A type class in biology is typical for a set of finches and maybe typical for a wider class of animals, namely birds. I think that doesn't work nearly so easily for mathematical models because they're abstract working objects like mathematical models. The representing gap is just much bigger. Right? We can easily see how finches might tell us something, a type kind of finch might tell us something about the family of finches more broadly. But when you have a mathematical model, there's a big representing gap. And so one has to think about the quality of typicality and where you're going to find it. And here I think there's two bits. First of all, in relation to other models, and only secondarily to a class of things in the world that it might represent. And I think the first is about internal validity, and the second is about the parallel validity. Right? So inferring from an experiment in the world of the model to other similar worlds in models, right, is the internal validity, and inference from the model to the world that the model's representing is this wider parallel thing. Here I want to go back to Edgeworth, who in his first discussion of something which became the Edgeworth box, talked about something as a mathematical induction. And it's a very interesting argument he made that by virtue of a single representative, particular, authenticated instance of mathematical reasoning without numerical data, so it's an abstract mathematical object here, is sufficient to establish the general principle. Well, this is a pretty heavy-going kind of combination of things, but it's a very unusual for the time kind of way of framing what was going on. And this is the beginning when mathematical economists are beginning to start building models. So we're not talking here about the Walrasian general equilibrium world, which Walras was building at the same time, or built at the same time. We're talking about Edgeworth having produced a little diagram and making this claim about what this little diagram could tell us. Now, the single representative particular case, authenticated case, so we've done our little mathematical reasoning, we've agreed that this is perfectly sound mathematical reasoning. Representative particular is somehow a kind to capture that this particular model is representative for a particular class of things. And the class of things that Edgeworth was arguing about was exchange relations in the Robinson Crusoe, Man Friday world of isolated exchange. Now, if we think about the scope of the Edgeworth box and the kind of mathematical reasoning that goes on in it, one can argue that there's a whole series of moves by which these results just get taken from that first one, in Edgeworth's case, to the next one in Bowley, the next one in Pareto, and a set of people who created the Edgeworth box as we now, its economists now know it, so that the mathematical experiments, the representative particular mathematical experiments that Edgeworth did, don't have to be redone again by the next economist who comes along. They can just be transported from that first version of the model into the next version of the model. Right? And from thence, they can be transported into extensions of the model as the model develops and as the model usage changes. It's a bit unclear what the general principle might mean here. What general principle is he referring to? And I think one of the ways might be to think about this is to think about the way geometric reasoning kind of works. This is diagrammatic reasoning. And there's a very nice book by Reveal Netz on how Greek geometry reasoning went on, which is to say, this geometry looks like the complete deductive way of reasoning. But in fact, when you look at the way that Greeks developed the arguments, what they were doing is saying, let's take a point here and see what happens if we take that point there and we make an argument about that point there. Well, which other points is this true of? Well, let's take a next point next to it and see whether it's true. So it's actually a whole series of inductions, or kind of proof by boredom. How many of these points do you need until you're convinced of the general principle by which any point in this triangle, for example, would give you this kind of result under this kind of transformation? So I think that there's something here like a model induction He's talking about a mathematical induction. I think there's a kind of model induction going on here, which enables the community to infer from model to model in the same domain, but then, for instance, when people change when economists move a kind of simple supply-demand model for a commodity into an argument about people's trade-off between labour and leisure, they're changing the domain of the model, they're making a model induction from the commodity space to the leisure and labour space. So something that comes with the model is a kind of internal validity about the reasoning that's already gone on in that model, which can be transferred not just into the sequence of the same model, but into analogical like models. And I think if you rethink now with this kind of framework, that's exactly what Samuelson was doing. He was trying out, first of all, different points on these parameters, trying out which ones worked, or what results you got, found that they were all wildly different, and only then trying to map out the general space within which one could make these model injections. So these are representative particulars here, which then he can't get into a general principle, so he has to figure out what the general principle looks like with a different mode of solution, but not because it's a different model. And the same is true if we think about Marshall's famous supply and demand curves. The representativeness here is somewhat different terrain. The representativeness here is that the world here, not the world in the model, but the real world here for Marshall, has different kinds of supply curves in it. Different industries have different kinds of supply conditions. Some have increasing returns to scale, some have constant returns to scale, some have decreasing returns to scale. And Marshall, I think under one reasonable interpretation, thinks that there's a whole lot of different types of industries in the world, and if you could figure out the different kinds of types and make a model for each type, you would have a set of models that would cover the terrain in the world. So that if you went to an industry and said, what's happening in this industry, and you knew which type of industry that was, you could then make sensible inferences about that type of industry based on your model for that type. Right? So it's a strategy which is like biology. It cuts up the world into types of things, and if you've got them all properly labelled and properly figured out, each of these models will give you the possibility of the parallel inference, or the parallel validity in that world. Right? So it's not that you've got a general supply and demand model, you've got always classes, types of models which might or might not apply. So the representativeness here is not in the world of the model to the next generation of the model, but each of these models is representative for a type of industry or type of firm. So the representative is going to the parallel validity problem. Okay, I'm getting towards the end. I'm going to be pleased. 3 more slides. Right, so of course this parallel validity problem is not without its difficulties, because some of these things might not exist. They might be empty. This is the classic argument. Well, the analytical worlds in the models may or may not act as representatives for types of phenomena in the world, because not all of those types might exist. It might be the case that some of these things they don't have any equivalence in the world. Right? We've made them up in the world in the model, and there's no reference point, there's no industries which fit into that, which is the argument of empty economic boxes. There are no industries of some of these kinds. So if they're not empty, if these representative particulars are each representative particular is not an empty box, then it might be that you can expand your inference from the world in the model to the world that model represents in a representative way. But it's going to be very restricted to just that class, not to everything else. It's not going to be a general inference, it's going to be restricted. So that's why I say it's not a generalizable inference, it's restricted, it has a space of possible inference, right? It's got a broader range than the lab, but it's quite vague. These are quite vague. There's no numbers on them, right? So all they've got is directions. So it's vague, and it's restricted to the class, but still it has that possibility of the inference space, right? Broader than labs, but vaguer. if that's the right way of expressing it. And not generalizable beyond the class for which this is a representative case. So, yeah. Models may be truth makers about the small world in the model. That's the internal validity argument. If you can make this world in the model, it offers you has revealing capacities, has dimensionality, it can make you truths about the world in the model. But not about the world that model represents necessarily. So the outcome is that learning about the models learning about the world from working with models, if we consider it as an inference problem, it's going to invite modest claims about how much we learn about the world from models, and deep skepticism about action in the world based on models. So we should be worried about using models as engines, not cameras, as in McKinsey firm. Now, okay, so you say, we know all this already. We know the bottom line. We know that you can get these nice little results in the world of the model. We know it's dangerous to think that the models are going to tell you things about the world. What I've been trying to do here is to say, yeah, but at least now we framed it as an inference problem, we've managed to get some space in which we can see why some inferences may be plausible and helpful, and why some of them are not going to be going to give us any kind of outcome. But even apart from that, we've also got some grip on how it is that models are going to have these revealing possibilities about the world and model, which might tell us about things we should be looking for in the world, which we wouldn't necessarily have thought about looking for without this experimental framework. Thank you.
Complete, enriching, here,
tour.
I want to ask you about the truth problem, or the truth, just a small problem.
What do you want to ask more exactly?
One of the options, the last one, about models, maybe truth makers.
About the world in the model.
Yes. And that is all, or you can extend.
That's the only place I think where I have truth in these presentations. It may have slept in somewhere else, but actually, no. There's nowhere else you can make truth in this framework, except in the bound, there's the internal validity, but the internal validity may not tell you anything about anything that's interesting. Right? I think that's true of the Samuelson. The Samuelson model is very interesting because it tells you that this model is totally inadequate because anything can happen. Well, a model in which anything can happen is giving you some truth, but it's useful to know that, but it's not going to be much use anywhere in the world.
Nicolas. Well, in English it's difficult, but
well,
I
you
will
try it in Spanish and get someone to translate.
Yes, my worry is about the relation between the models and the real world. You use the parallel validity, different with the lab, the experiment of the lab, but that external validity.
Yeah.
I remember that Cartwright used external validity in two cases, and when you say parallel validity, I thought in Sugden that Sugden or
credible Sugden.
Sugden used parallel and induction, and these two, Sugden and Cartwright, are two different views of the relation between the model and the real, and which is the winner or which is...
That sounds like a truth question. Okay, so I find it useful to distinguish between parallel and external because I want to make this point about how limited lab experimental inference really is. Because I think people don't appreciate how limited it is. That how really, if that you know something about, you've done this experiment in the lab, you've learnt something, you've repeated it again and again, and you're sure it's true, in your truth-making. I mean, again, truth-making within the world of the lab is the same kind of problem. You may not get it the first time, but after many repetitions you might get it. And then in the world which is not in the lab. So I don't think a lot hinges on me calling this parallel and her calling this external, except I wanted to make the point about lab science versus model science.
So the relation between the models and the real is more difficult than between the labs and the real world.
I actually think they're both difficult. I mean, I think my father was a lab scientist, and I learnt from him that, for instance, you know, I mean, a whole lot of objects go from, you know, solid to a liquid to a gas. But if you actually want to use one of these things, you've got to go and chart out exactly the process and the time and the temperatures and everything else. So there's a generalizable kind of finding, which presumably took many decades to establish that this was true in a very general set of class of things. But it still doesn't mean that you don't need to know the particulars for that particular thing if you're going to use it somewhere. So I don't think that the lab experiment external validity, and it's not philosophically easy, I think, to frame, and I think there's interesting work by Dan Steele on this, and interesting work by Francesco Guala in the case of economics about the kind of reasoning that would get you there. But, so all I'm trying to do with the different terminology is say it is slightly different here, it's parallel. Now the Sugden case, Sugden, I think, uses it for a different reason, which is he wants to have these agent-based models outcome. Somehow he wants to be able to get the outcomes of those kinds of model experiments directly mapped onto the world. So without actually figuring out any of the causal structure that would actually get these outcomes. So I think that's a different reason for using parallel, because he thinks of them as, you know, these parallel worlds, right? So that's, and I don't really, it's the same problem. I don't think his solution quite gets us there. I don't think he can do quite what he's saying, but it's the same kind of idea. Yeah.
Okay. I don't think go. The model is a very, very expensive notion.
Yeah.
There are other things or concepts, the methodological importance that are not models. Always models.
Sorry, all his models.
Always model, or there are other things or concepts that are not model.
In economics.
Mm-hmm.
Yeah. What do you have particularly in mind? Data? Facts? Theories?
Facts.
Yes,
and the different theory and model.
I think it's really problematic now to figure out where the line lies. You know, economists will talk about the law of supply and demand still, although to all intents and purposes that's a kind of very generic, general sort of stuff, which as soon as they want to do anything with it, they're going to start talking about models. Right? And then there's the quantity theory of money, which is kind of proper theory, which, you know, has a thesis about causality, and it's supposed to be general and whatever. And then there's things like game theory, which is a whole approach. So I don't think there's a good line for economists between theories and models. And theories might be somehow a little bit more general, a little bit more hypothetical. I don't think it's easy to say. I tend to think of Walras having a theory and Marshall having models, because it's something about not the scale that's mattering here, but the method of approach in which the Walrasian world is one in which there's the whole everything is postulated, and then it's a problem of solving this in a kind of hypothetical postulation and proof regime. And I think of that being different from models, which is this workable sets of instruments, tools, and I think of them as different because of the work of Hacking and Crombie on epistemic genres, which separates out historically the development of mathematics, the method of postulation and proof. You postulate something, you prove something. Again, truth in the world of mathematics. From analogical and hypothetical modelling, which has its roots in astronomy and those little mechanical models which people turn the handle of and see the planets going round, which is not postulation and proof, it's a modelling tradition. So I think there are two traditions, both using mathematics, which makes it difficult historically to pull them apart.
Would you say that there's any kind of quality that a model should have, like in order to predict the future, reality? Or would you say that a model that has more variables and parameters are more useful to use it in practice, reality, or?
Is this about the scale and the dimension problem?
Yeah.
Yeah, it depends on the purpose, right? I think at one stage central banks just had large macroeconometric models, and I think more recently, I don't know if there's anybody from the central bank to tell me what their models, but at a certain point, maybe 20 years ago, maybe 15 years ago, a lot of them gave up these big models. So they have a short-term forecasting model, which is basically a time series descriptive model for